video, I'm going to walk you through the derivations that involve the gas laws, and we are going to be looking at Boyle's law, Charles' law. We look at Avogadro's hypothesis. We look at the combined gas law. Look at Gay-Lussac's law, Dalton's law, partial pressure, Graham's law of diffusion, and Graham's law of effusion. So let's start with Boyle's law. Boyle's law, and I'm going to abbreviate that as BL. Boyle's law Boyle's law talks about the relationship that exists between the volume and the pressure of a gas. Boyle's law talks about the relationship that exists between the volume and the pressure of a gaseous substance. And the law states that the volume of a fixed mass of gas, is inversely proportional to its pressure. This is Boyle's law. V here represents the volume, and P here represents the pressure. And 1 over P here is an inverse relation. So V is inversely proportional to its pressure. And what is happening here? When you increase the volume of a gas, the pressure decreases. And when you increase the pressure of a gas, the volume decreases. If you increase the volume, the pressure decreases. And when you increase the pressure, the volume decreases. So for Boyle's law, if you increase V, that I'm going to use this arrow that shows increase, that is going up, then what happens to the pressure? The pressure moves down. That's vice versa. If you increase the pressure now, what is going to happen to the volume? The volume is going to decrease. Okay, so for us to establish the mathematical relationship that exists here, we say V. So this implies that our V, we are going to remove this proportionality symbol here. And if we remove this, we add our constant K. And if we add K, you're going to multiply K with 1, and that is going to be K. So this will be equals to K over P. Okay, we've removed the proportionality symbol, and now we've added our constant K. So this will be like cross multiplying. If you cross multiply, let's say we have 1 here, then this multiplied by this. V times P, K times 1. So if you multiply K times 1, then it's just K. Equals, if you multiply P times V, then it is what? PV. So K is equals to what? PV. We've established a relationship for the constant K. But when we talk about gases, always we look at 2 states. We have the initial state and the final state. And that's the same as having initial conditions and final conditions. So if our K, that the initial conditions, K1, equals what? P1, V1, then the final conditions will be equals to what? K2, and this will be P2, V2. So the initial conditions or the initial states is always equals to the final state. So K1 will be equals to what? K2. So if K1 is equals to K2, you know what K1 is? K1 is equals to P1 V1. K2 is equals to what? P2 V2. So K1 is what? P1 V1 equals to, what is our K2? K2 is P2 V2. P2 V2. So this is the relation for what? Boyle's law. If you're asked to solve any problem that has to do with the pressure and the volume of a gas, this is the relation that you're supposed to use. You'll be given, maybe they will give you initial pressure. Let me just write this down. P1 represents initial pressure. V1 represents initial volume. P2 represents the final pressure. And V2 represents the final volume of the gas. So anytime you see a question whereby you're given 3 of these and you're asked to find the one, what you need to do is for you to divide and ensure that, suppose you're asked to find P1. If you're asked to find P1, ensure that P1 stands alone. So you divide here by V1, you divide this other side by V1. So the V1 is going to cancel this V1 here. You're left with P1. If you're asked to find P2, you divide this side by what? V2. You divide this side by V2. So the V2 is going to cancel this other V2. You'll be left with P2. So that's how you use it. So the other law that we are going to talk about is what we call Charles's law. Let me just spell it. This is called Charles's law. Others call it Charles' law. Yeah. So for Charles' law, this deals with the relationship that exists between the volume of a gas and its temperature, its absolute temperature. Because when we talk about absolute temperature on a Kelvin scale, we are referring to the temperature being either 0 degrees Celsius or 273 kelvins. So the relationship for Charles' law, say V is what? Directly proportional to what? T. The volume and the temperature has a direct relationship. What does that mean? If you increase the volume of a gas, then the temperature is expected to be increased as well. If you decrease the volume of a gas, that is V decreases, the temperature is also going to decrease. If you increase the temperature, then the volume is also what? Going to increase. That is a direct relationship. The volume of a fixed mass of gas is directly proportional to what? Its temperature. So V is directly proportional to T. So if we remove this proportionality symbol here, we add our constant K. So this implies that V equals what? KT. So what is going to happen? We try to make K the subject, and in making K the subject, we divide here by what? T. We divide here by T. So this cancels this. So here we are left with what? K, and here we have V over T. So K will be equals to what? V over T. K is what? V over T. As I stated earlier on, we have initial conditions and final conditions for a gas. So we have K1 to be equals to V1, K1 to be equals to V1 over T1, and K2 to be equals to V2 over T2. So if K1 is equals to V1 over T1, K2 equals V2 over T2, and definitely we know that always the initial conditions K1 are always equals to the final conditions K2. So K1 equals K2. So we know what is K1. K1 is V1 over T1. So V1 over T1 is equals to V2 over T2. So this is the relation that we can use to solve problems that has to do with Charles' law. Anytime you see a question on the gases and you're given volume and temperature, then always remember to use Charles' law. That's the only law that you can use to solve that particular problem. V1 T2, that if you cross multiply, you're going to get V1 T2, V2 T1. If you're asked to find any of them, then it's just a matter of dividing. What am I saying? If you cross multiply V1 times T2, this is V1 T2, this will be equals to V2 T1. Yeah, if you have this relation now, then it's very easy for you to find either of these parameters. If you're asked to find the initial volume V1, then you divide it here by T2, you divide it here by T2. So the T2 is going to knock this off. You'll be left with what? V1. You can try doing that on your books, please, so that you understand what I'm trying to say. So this is the relation that exists for Charles' law, not this. This is the relation. V1 upon T1 equals to V2 upon T2. But if you want to find any of these, you cross multiply so that you can have an established relation that you can use to find any of these. So now let's move to the combined gas law. Combined gas law. Okay. The combined gas law has to do with Boyle's law and that of Charles. Combined gas law has to do with Boyle's law and Charles' law. We know that for Boyle's law, that BL, we said what the volume is inversely proportional to its pressure. V is inversely proportional to what? Its pressure. And for Charles' law, we said the volume is directly proportional to the temperature. So if you look at these two relations here, you'll notice that on the left hand side we have V, here again we have V. On the other side we have 1 over P, and here we have T. So you notice that on the left hand side we have the same thing, which is volume. So in essence, it means that the volume is directly proportional to the temperature and inversely proportional towards its pressure. So if we establish a relation for Boyle's law and Charles' law, it is in this form. V is what? V is directly proportional to T, as we can see here. So we write T at the top. And inversely proportional to the pressure. So we have T over P. This is the relation that we can use. Always we remove the proportionality constant or the proportionality symbol. So our V will be equals to KT over P. So if we cross multiply, P times V is going to be PV equals KT. What do we want to do here? We want to make K the subject. So in doing that, we divide here by T. We divide here by what? T. So this cancels this. Yeah, this cancels this. So our K will be equals to PV over T. But we know that we have the initial state and the final state of a gas. So I've already explained here some of these parameters. The only thing that I didn't include is the temperature. And we should know that T1 is the initial temperature and T2 is what the final temperature. So K1 is equals to P1 V1 over what? T1. And K2 will be equals to what? P2 V2 over T2. And we know know that the initial conditions are always equals to the final conditions. K1 equals to K2. So this implies that our P1 V1 over T1 is equals to what? P2 V2 over T2. So this is the relation for the combined gas law. So anytime you're asked to solve any problem that has to deal with pressure, volume, and temperature, this is what you're supposed to use. And for you to establish a direct mathematical relation is for you to cross multiply this times this times this. Then you're going to get a relationship. And when you get that, the next thing that you need to do is for you to divide. When dividing, ensure that the parameter that you want to find stands alone. When you cross multiply, you're going to get P1 V1 T2, P2 V2 T1. So suppose you're asked to find P1, you divide by what? V1 T2. If you're asked to find P2, you divide by what? V2 T1, both on the left and the right hand side. Let us look at another law, and that would be the Gay-Lussac's law. Gay-Lussac's law. Gay-Lussac's law talks about pressure and temperature. And here we have a fixed volume. If the volume is fixed, then the pressure is directly proportional to the temperature. So P is what? Directly proportional to T at a constant volume, keeping V constant. So this will be equals to, P now will be equals to what? KT. In making K the subject, we divide here by T, divide here by what? T. So this cancels this. So this now implies that our K is equals to P over T. Remember, we have, as always, we have the initial state and the final state. So K1 is equals to P1 over T1, and K2 is equals to what? P2 over T2. So K1 is equals to what? K2. So this implies that we know what K1 is. It is P1 over T1, and we know what K2 is. K2 is what? P2 over T2. So this is the relation that we can use to solve problems under Gay-Lussac's law. Okay, so the next thing that we are going to look at here is Avogadro's hypothesis. Avogadro's hypothesis. This is not a law. Please don't misunderstand this to be a law. It's an experiment that Avogadro carried. And when he carried out the experiment, he noticed that the volume of gases, that is gases that behave ideally, and you talk about ideal gas, it's a gas that obeys the gas laws. So he noticed that the volume is directly proportional to the number of moles. At a constant temperature and pressure, the volume is what? Directly proportional to the number of moles. So here also we can establish our relation to be V equals Kn. So if we divide here by N, this knocks this off. So this implies that our K equals V over N. So our K1 will be what? V1 over N1, and K2 will be what? V2 over N2. Well, we know that our K1 is always equals to K2. Yeah, so K1 is what? V1 over N1. K2 is equals to what? V2 over N2. this is the relation that you can use to solve problems under Avogadro's hypothesis. Anytime you see a question that has number of moles in it and has volume, then you'll be able to solve it. But it doesn't always mean that they will give you number of moles directly. Sometimes they'll give you the mass of the gas and they give you its volume. So they'll be expecting you to find the number of moles. Then after that, you substitute the value into the expression. We know that in that case, if you're asked to find number of moles, it will be the mass over what? The molar mass. Okay. So let's look at another aspect that is very, very important, and that will be the ideal gas equation. Ideal gas equation. Yeah, ideal gas equation. First of all, we need to understand what is an ideal gas. An ideal gas is a hypothetical gas that obeys all the gas laws. It obeys Boyle's law, Charles' law, Gay-Lussac's law. It obeys Avogadro's hypothesis and all. So let's try to bring out all of the relations of these gas laws. So we know that Boyle's law, that's BL, the volume is what? Inversely proportional to its pressure. And for Charles' law, we know that the volume is what? Directly proportional to the temperature. And we use Avogadro's hypothesis that says the volume is what? The volume is directly proportional to the number of moles. So if you look at all of these relations, you notice that here we have V, and here we have different relations. But we know that the volume is directly proportional to the temperature. At the same time, the volume is what? Directly proportional to the number of moles. So this will be at the top and we have P at the bottom. So if we use one relation, it will imply that our V is what? Directly proportional to what? Number of moles and the temperature, NT. You notice that we have this as direct relations, and the pressure is an inverse relation. So this is it. So here we are not going to deal with K. We are going to introduce the gas constant, which is called R. R is the gas constant. Gas constant. Yeah. So instead of using K, we use R. So V will now be equals to what? R and T over P. So here we are not going to make R the subject. We establish a relation between pressure, volume, and number of moles and the temperature. So we cross multiply. P times V is what? PV. So PV equals to what? If we arrange this, we are going to get nRT. So this is the ideal gas equation. You can actually use the ideal gas equation to obtain all of these relations, keeping certain parameters constant. But after this video, I will also prepare a video on that to show you how to use the ideal gas equation to obtain all other relations that has to do with gas laws. Okay, so we're going to look at what we call the Van der Waals relation, because there are certain gases that deviate from ideal behavior. We have certain gases that deviate from ideal behavior, and these gases are called real gases, and they are not called ideal gases because we have some. So Van der Waals made a correction that accounts for the intermolecular attraction and the extra or the excess volume that exists in a gas. So say Van der Waals equation. And for Van der Waals equation, if you are given a question to solve under this aspect, they will always give you the constants for A, that is the intermolecular attraction, and they give you B, the extra volume that exists in a gas. So it is P plus AN squared over V squared into N minus B, all equals to nRT. So A accounts for the intermolecular forces that exist between the gas molecules, that's for real gases, and B accounts for the extra volume that exists in the gas molecule. So if you look at the two relations here, we have PV equals nRT. So the correction was only made here between the pressure and the volume. So that's where we established AN squared over what? V squared. And this is the correction, because here we had only P and here we have V. So this should be V minus NB instead of P, V minus NB. So that's where the correction is made here, the pressure, and also here for the volume. So this is Van der Waals relation. So we are going to look at another law, which is Dalton's law of partial pressures. Dalton's law of partial pressures. Dalton's law of partial pressures. This law has to deal with the interaction of different gases within a cylinder or whatever system that we have. And you can have different gases interacting with each other. And this law states that the total pressure exerted by a mixture of gases is equals to what? The pressure exerted by each gas within a cylinder. It is equals to the pressure exerted by an individual gas. That is what gives us the total partial pressure. Suppose we have this here, PT, that is the total pressure. This should be equals to what? P1, that is the partial pressure of gas 1, plus P2, partial pressure of gas 2, plus P3, partial pressure of gas 3 to infinity. It depends to the number of gases that we have. And for short, PT is equals to what? The sum of what? The individual gases, Pi. This is the sum of what? The gases that are present. So if we relate from the ideal gas equation, PV equals nRT, we try to make a relation for what? P. So pressure now will be equals to what? nRT over V. From here, I will divide by V. Here, you will divide by V. So this is the relation for pressure. So what are we to do? We substitute the value of pressure here into this relation. So now PT will be equals to, anywhere we see P, we write nRT over V. But P1 has number of moles 1, because R can be constant, T can be constant. We can possibly have a constant volume as well, but the number of moles is going to change. So the first one will be N1 RT over V. That's for P1. For P2, we have what? We're going to get N2 RT over what? V. For N3, for P3, we are going to get N3 RT over what? V. So if you look at these, you notice that we have a common term. Common term is RT over V, RT over V, RT over V. The only thing that is changing is what? The number of moles. So we are going to factorize the NT, the N. We are going to factorize RT over V out. We'll bring it outside. So if we remove RT over V here, we'll be left with N1. You remove RT over V here, we'll be left with N2. You remove RT over V, we're left with what? N3. So this will be what? Into N1 plus N2 plus N3. Yeah. So this is one of the ways. But if we let our N, let's say Ni equals to N total, that is Nt represents the total number of moles, Ni represents a certain mole. It can be 1, it can be 2, it can be 3. So if we replace this N1 plus N2 plus N3 with Nt, then our Pt now would be equals to RT over V into what? Nt. So this will be the same as Pt equals to what? Nt RT over V. So this is the relation that you can use if you're asked to find the total pressures of what? A gas, using Dalton's law of partial pressures. P total is equals to N total multiplied by RT over V. This is the relation. So let's look at another aspect that has to deal with the pressure fraction. Pressure fraction. Pressure fraction. For the pressure fraction, suppose we have gas X, a gas X, then this will be equals to Px over what? Pt. Where Px represent the pressure of gas X and Pt represent the total pressure. We also have the mole fraction of a gas. Mole fraction. The mole fraction, let's say we have a gas X. This is also equals to the number of moles of gas X over the total number of moles. This is not difficult. If you have a gas X, then you're asked to find the mole fraction. It is the number of moles of the gas X over the total number of moles of all the gases that you have in the mixture. We have a relation that exists between mole fraction and partial fraction. Mole fraction and partial fraction for gases. So we know that Px is the number of is the pressure of gas X. This will be equals to number of moles of gas X, that's moles of gas X, multiplied by the total pressure. If you're asked to find the pressure of X, it is the mole fraction, this X here represents mole fraction, multiplied by the total pressure. That is going to give you the pressure of gas X. And we must also know that for a mixture of gases, let's say we have gas X, gas Y, and gas Z, you should always know that the pressure of X plus the pressure of XY plus the pressure of what? XZ must always be equals to 1. This is another area, another key concept that you need to understand. So the last thing to look at here is Graham's law. Graham's laws of diffusion and effusion. First of all, you need to understand what diffusion is in this aspect. If you're asked to state the Graham's law of diffusion, that has to do with the rate of a gas, the rate of formation of a gas. For diffusion, Graham's law of diffusion, let's use this other part. Graham's law of diffusion states that the rate of diffusion of a gas, R, is inversely proportional to the square root of what? Its density. We often use the symbol rho. The rate of diffusion of a gas is inversely proportional to what? Its density. So here we can have R equals to what? 1 over, let's use the density, but the symbol is rho. So is equals to the square root of the density. We can have two gases like Rx and Ry within the mixture. So this will be Rx over Ry is equals to what? Square root of d over d. This can be d1 over d2. This is Gram's law of diffusion. Rx over Ry is equals to the square root of d1 over d2. Effusion. The only difference between effusion and diffusion is here we are dealing with the rates of diffusion of a